production. This is going to be delivered by Matt Robbins, General Manager of Power Capacitors Limited. Thank you very much for joining us this evening.
Thank you. Good evening. Like you said, I'm Matt Robbins from Power Capacitors, here to talk to you about power quality. Strap in. Next frame. Okay, I work for Power Capacitors. We've been in Birmingham for 50 years. We're a family-owned company manufacturing power quality solutions. This has taken on different dimensions over the last 10 to 15 years with the introduction of variable speed drives and more electronic controls. Okay, so we have a quick look at how electricity is done. Okay, we have a generator, goes to a step-up transformer, goes over to the transmission line, step down, and then there in the corner are us, the consumers. So we generate at kilowatts, transformers will be rated in kVA. The lines will have losses in them. We have another transformer here rated in kVA again, and we pay for electricity in kilowatt hours. The kilowatts here are not necessarily the kilowatts that we actually pay for, and that's what we're going to talk about today. So, next slide, please. So, kVA supplies both kilowatts and kVAR required by the load. So, on the primary side of this transformer, we have all the current and losses generated here, and this is being drawn by the consumer's loads here. So anything we can do to save current here will save generation here. It seems obvious, but since we split up the electricity boards, this has fallen down. What people actually try and sell the generation here, they sell to these guys, you sell to the district, who then sell to us. The people who sell to us want to sell in kilowatt hours. They're not interested at all in the losses in the system here. Now, this is where people are going to start trying to claw back money from us in the next 10, 15 years. They're going to try and get this part back onto us paying the bills. At the moment, it's hidden. The moment it's behind BUOS, TUOS, basically anything they can think of to try and hide this loss here. That's why a lot of the companies that were selling us electricity went out of business. They didn't realise that they were paying for 10, 15% of the electricity generated here that they weren't charging us as consumers. Not a big problem when you're someone like Octopus or someone who knows what they're talking about, but when you're a guy off the street and he's just gone, well, I can make some money here. All I need to do is put 5% on whatever the generating guys are doing. I can make my money. That's why they all went out of business. The quality that the suppliers have to give you guys is covered by EN 50160. This basically tells you that we're going to give you 240 volts plus or minus 10%. I'm going to give you 50 hertz plus or minus 0.5 of a hertz. I can disruptability, not a word, but how often they can brown out, black out, supply you with 30 minutes, no electricity. That's all covered under this agreement. But you agree to the power quality. So anything you do on your supply has an effect on the supply that's on the grid supply. So you agree not to mess up the electricity too much. Have the next slide, please. Consumer loads come in various different flavours. You have a resistive load, which is what we did at school. Inductive and capacitive loads. So inductive motors, capacitors are used as an energy storage. Then we have active loads, inverters, switch mode power supplies, frequency converters. They've becoming a lot more commonplace in the last 10 years. So all loads are made up of those three components. Inductive loads primarily resistive and inductive. Capacitors obviously capacitive. Kilowatts and kVAR can be negative. We can export them to the grid. Embedded generation is becoming more and more popular. So CHPs. Also, we're starting to get more EV, and that's going to introduce another complexity to it. You're going to have DC coming back onto the grid, or not directly, but so I'm not quite sure how that's going to impact grid security. Next one. Okay, this again just a simple explanation of the different loads. So we have an inductive load. And an inductive load current will lead voltage. The phase angle between these two is called power factor. In a capacitive circuit, voltage leads current. So ideally, we'd want this to be a resistive load. Here, we've got a power at the voltage that's lagging. Here, we've got a power at the voltage that's leading. So we've got two sets of power that we don't really want to pay for. We only want to pay for one set of power. That's what we talk about when we've got a power factor of unity. These would actually, the red line there would be overlaying the black line there. So next slide, please. So what does this mean actually in real life? Well, kVA, if you remember, was what we measured the transformer in. Kilowatts is what we're actually using from the transformer. kVAR is a reactive power. So what's the reactive power? Well, in a motor, it'll be the magnetizing current. So it'll be the magnetizing current the motor needs to run. That's being supplied at the moment by the transformer. What we can do is we can introduce kVAR capacitors locally. So you're not having to get kVAR off the mains. We can have it supplied locally using the bank. So the kVA suddenly equals kilowatts. We get a unity. We're not getting two lots of power. We're only paying for one lot of power. We're just paying for kilowatt hours. So what does this mean? Well, we can rate the transformer lower. We can save extra current on the cable sizes and losses in the transformer. Reduce the voltage drop. When we put voltage across a reactor, the voltage will drop, so we can get rid of that. Then any increases in kilowatts we can probably get through the transformer. So next slide, we've got a little worked example. So say we've got a factory with a 630 kVA transformer and we want a workshop to work at 500 kilowatts, and that operates at 0.75. kVA the load requires is 665. Obviously more than the transformer. We've got losses in the cables. The transformer is overloaded. We can't run that 500 kilowatts. However, if we install 250 kVAR and improve the power factor 0.75 to 0.93, this equates to 537 kVA. We've saved that amount of power. Losses come down. We're only using 35% less power than we were in here. And now the transformer can support that 500 kilowatts of load, but we've also got 15% spare capacity. So by installing those 250 kVAR, not only can we run that load, we can actually put another 50, 60 kilowatts on it. Go to the next slide, please. Okay, harmonics now. This is the big one that everyone's interested in at the moment. The harmonics are being generated by basically any new load. So switch mode power supplies, LEDs, variable speed drives. And this is creating currents, harmonic currents on the system here, which induce a harmonic voltage. Now the harmonic voltage is being put onto the transformer and being put back on the grid. So instead of having a nice smooth voltage that the supplier can give you, this is being distorted by the users. So you've agreed to a G55 engineering recommendation to be connected to the grid. The distortion you're allowed is 5%. The distortion that the supplier is allowed to give you is 8%. It's basically because they've got lots and lots of people using 5% and they want to give themselves some headroom. So they've agreed to an 8%. Come to the next slide, please. So these are the active loads, the harmonics. Active load is anything where there isn't a direct link between the current and the voltage waveform. So anything that is an inverter where they take an AC voltage, turn it into a DC voltage, and then either use that as a direct current or change that back into a controlled AC voltage. This is where the problems arise. So your variable speed drives, so there'll be water pumps, your compressors, things like that. UPSs, switchable power supplies, which are printers, servers, especially LED lighting, welding machines, battery chargers. You guys, arc furnaces, induction furnaces, static frequency converters, rectifier units. So basically anything that you've bought over the last 10 years is basically harmonic generating. It'd be really unlikely you bought a DOL or Star Delta motor in the last 10 years. So this is basically the setup. This is your loads. So you've got lots of different loads. You've got linear loads, computers, some lamps, variable speed drives, and you've got your rectifier arc furnace. Harmonic generating, harmonic generating, harmonic generating, harmonic generating, not harmonic generating, but these all add up into this bus level here. This gets put onto the transformer, and this is transformed up onto the grid. This is why the grid suppliers, the network operators are getting very, very tetsy about it, because, if you can go to the next slide, putting the harmonic voltage onto the grid gives other people problems. So if you're sharing a transformer with someone like you do at home, and someone puts a big rectifier on, and in the old days you used to know if you switched on an immersion heater next door, your lights would flicker. It's a similar sort of issue. If someone puts on harmonics, you'll get an effect from them. So resonance, you've got potential amplification of current at certain frequencies. I'll show you what that is in a little while, because it's easier to show you. You've got increased losses due to the extra harmonic current being carried in the cables. You've got the standard 50 hertz joule effect going through the cables, but you've also got the RMS increase to high frequency. So the higher the frequency that the current's going through the cable, the more heating effect it has on that cable. So something at 50 hertz with 10 amps, it's probably got the same heating effect as something at 500 hertz at 0.1 amp. It's that sort of effect. So the higher frequencies you get, even though it's lower power, you've got more and more heat going through those cables. So you've got heat going through cables, they're probably undersized. Also, the heat is going to go into your breakers, so your breakers can get overloaded, especially if they're temperature sensitive, which old breakers are, and probably what you've got fitted. So losses in induction motors, it's a 8% THDV, so that's quite high to be fair. You're going to get losses or increased losses of 5%. This means that the variable speed drive isn't going to work as efficiently as it did. The way that harmonics work in a variable speed drive is that some of the harmonics are going to try and speed up the motor, some are going to try and slow down the motor. Depending on that level is how efficiently that inverter is going to work. I've put this in there. Schneider have said if you've got THDV of more than 10%, you're going to have a problem with your inverters. I've seen it once. Most places I've gone to where there's more than 10% have had different issues. Inverters aren't one of them, but I've included it here. Distorted waveforms can cause regulation devices, computer hardware and control protection relays to operate incorrectly, because we're overloading them with currents that the engineer didn't expect to see when he designed it. We're going to get nuisance tripping. And then uninterruptible power supplies are going to overload because they haven't been the current harmonics haven't been taken into account. So if there's this extra current in the system, the UPS is being asked to supply for it. It's supplying the load that it thinks it needs to supply, but there's extra currents in the circuit. The UPS will try and feather back because it doesn't need to produce so much current, and the 50 hertz load will fail. So you have problems with the UPSs there. Transformer losses, again, it's the same as the losses in cables. The harmonic current is going to put more energy into the transformer, and we'll overload it. Safe limit for harmonic current distortion is 5%. Anything more than that, and we're expecting the transformer to start dying. That isn't a lot. We'd expect a normal VSD to run about 20-25%. So if your whole active load is more than 40% of the transformer rating, your transformer should be derated as well. Well, when was the last time anyone actually added up everything that was on the back end of a transformer and checked it against the transformer? No one does. Backup generators will need to be derated because they're going to be carrying another 30% potentially of current. And then your neutral conductors will start seeing harmonics at the 3rd, 9th, 15th. Normally your neutral won't carry any current. If it does, it'll be very, very small. So your neutral tends to be half the size of your phase currents. Unfortunately, if you've got harmonics, they're going to put twice the current of the phases down there. So you've got potential to burn out your neutral cables. Okay, so you lose your neutral cables, you start losing parts of your building, parts of your supply. So you're going to lose basically the ability to work. Energy losses, high losses in conductors, transformers, equipment. You're going to be paying for that because your transformer isn't working as efficiently. Utilities network operators will request remedial effects for harmonic currents. Okay, the engineering recommendation G55. If you're outside those limits, they can just switch you off. They can say, right, we don't want to supply your power anymore. I've seen it happen once in 30 years. So they want to sell you electricity, they're not going to switch you off. But what they will do is they'll keep badgering you to fix the issue. What I'm hoping to show you here is that it's in your interest as well to fix the issue because you will get payback from fixing your power quality. You won't have to derate your equipment. Generators, UPS transformers won't need to be oversized. Reduce service life. THDV of 10%, estimated equipment reductions are for single-phase machines. You're going to lose a third of the life for having a high THDV. Three-phase machines, 20%. Again, I don't quite believe that figure, but it's a Schneider figure. So 5% for transformers, I can well believe. We've seen quite a lot of failures on those. So to maintain the expected service life, you can be overrating all the time. So it'll go back to the good old days. If you want 50 horsepower motor, use 132 horsepower, really derate it, and it'll last forever. Nuisance tripping in the factory, heating in the cables, extra harmonic currents, you're going to overload your breakers that have been carefully designed by some engineer 30 years ago who didn't know this was going to happen. So the nuisance tripping is something that you do see. Equipment that's designed to IEC 61000 assumes there is a maximum harmonic currents at each harmonic level. If you're outside that, equipment that meets these is probably not going to work. So you're going to get nuisance tripping of those. All of those is probably every single phase inverter that you've got. And the second one is up to 75 amps. So it's quite a big inverter that you're going to be losing potentially if you go outside those limits there. And lastly, increase CO2 emissions due to the extra loading out through the supply grid and the extra generation required. So everything that we're adding to this, we're adding to the generation, we're adding to the CO2 that we're emitting. Okay, so what are the issues with specifics? So on induction furnaces, harmonic distortion, a distorted waveform impacts the efficiency of the furnace. I've got a couple of waveforms to show you in a bit, which will show this quite well, I hope. Voltage fluctuations, rapid flicker. Again, that's going to impose on the frequency that you're trying to run this induction at. We could have little hiccups. So instead of having a nice smooth frequency waveform, the input waveform is going to be chopped, it's going to be distorted. Put distorted in, you're going to get something distorted out. So you lose the efficiency of your furnace. So it's going to take you longer to heat something up. I'm guessing for you guys, time is money. So I'm guessing that that's a bad idea. Poor power factor, increased bills, reduced capacity in the system causes voltage drops. Keep your power factor high. keep your voltage up high, you'll not lose time. You'll keep the power high. That's what we're after here. So induction furnaces are pretty good if energy efficient, but low power factor and high harmonics reduce the overall efficiency. Power quality will put wear and tear on electrical components, lead to more frequent maintenance. Again, it's just going to cost money again. Okay, this is a particular issue they had in Colombia, which is how difficult it is to get information about your your industry. So they've got an arc furnace and a ladle furnace. The problem they had here was high flicker, high reactive power demand. It was the overnight implementation of grid codes. In Colombia, one Monday they went, everyone's got to meet 8% THDV. Across the board, make it happen. You've got a year to do it. So these guys, Paris, 26 point, rating about 0.6 power factor. So very, very low power factor. And the way that they had it set up was that they were causing quite a lot of flicker. So I think it was about 3 to 4 PST. Maris came up with a StatCon system, which is basically power factor correction with a little bit of filtering. So what they did was they corrected from 0.6 lagging to 0.9. This gave an increase in active power because they freed up the transformer availability. They had a reduction of 7%, but something they weren't expecting was a decrease in tap-to-tap times. No one was expecting this. They won't put a figure on it, but I imagine it's significant for them to actually include it. I think I know why, and again, I'll explain it in a bit when we see the waveform. So again, general electric furnaces, gives grid compliance, flicker mitigation, harmonic filtering, reactive power compensation, all done at 26.4 kV. It's a bit of kit, to be fair. On site, they got grid compliance to carry on working. So at the end of the day, everyone was happy. Okay, so this is a couple of waveforms now, and I think this is where the putting crap in, you get crap out, comes into it. We've got typical VSD loading. This is a factory in Hull. It's got refrigeration, main refrigeration. So what we have here is variable speed drive current form. Absolutely no problem. We're expecting a sine wave, but the way that inverters work, they chop up the wave and we get this distorted figure. What we've got here is an inverter not quite firing properly. What that does is it distorts this waveform. What we want from this waveform is a nice sine wave. You can already see that the distortion here is causing distortion on the nice sine waves. Got bumps there, but here we've got a huge distortion. Problem with this is that instead of having a nice voltage going around like that, we're losing those volts. So 1, 2, 3. And in 50 times a second, you lose that much. Now that might only be 1% of your voltage wave, but all the time, that's 1% down you're on your quality. So that's 1% down you're on your times of what you're putting out on your induction furnace frequency. So if we, next slide. Okay, so like I say, we've got just, this one's a good one because that's almost a square wave. So putting a square wave on a bit of kit that's expecting a nice smooth sine wave, cause that stress. So not only are we sort of losing the power there, we're putting extra stress on the electrical components. Again, there's another little misfire. So it could be an inverter, but as far as the customer's aware, everything's working fine. There's no misfires, there's nothing going on, but we're showing that his efficiency is down. His efficiency is probably down at about 2% on his whole supply there. Fixing that, we can improve that straight away. Okay, this one is a rectifier circuit. This is a BMW mini plant. They've got a huge issue here. This is meant to be a sine wave for your voltage. We've got so many problems here, it's untrue. This is part of the resonance circuit, resonance that's being set up, and a lot of harmonics. This is what we're expecting from a rectifier. It chops up the voltage because it's charging up capacitors to use as a DC supply. So whereas this is meant to be a sine wave as well, we're sort of expecting it to be chopped up. We're not expecting this to be a voltage waveform. Now, this voltage waveform isn't just being seen by the rectifier, it's being seen by the whole plant. So everything on your plant that's connected to this bus bar is seeing that voltage. So instead of that nice voltage that we're expecting, all the components are seeing a lot more. And this, to a component, this looks like an increased frequency. So it's not seeing 50 hertz, it's seeing 50 hertz times 5, so 250 hertz. It's seeing like 5 times the power it's expecting to see. Next slide. So, so what's happening here is that if you are heating something up, it's not receiving the power it needs to heat up. So it's going to take longer. Anything's going to take longer now, especially to do with heat. So even if that was put through a resistor, you've just got a standard, blower heater, it's not going to feel as hot with that waveform as a proper sine waveform. So is what we call 0 point triggered. So an IGBT, which is basically the switch that controls power in a lot of inverters and a lot of furnace applications, will use the 0 point because it's the only time that a sine wave on a voltage will go through something. So it will go, right, as long as it's going up and goes through the 0 point, I'll switch. I won't switch on the way down. On the 0 point going up, I'll switch. Problem when you've got a distorted waveform like this is that if that goes below that 0 point and goes up again, it'll try and switch twice there. Similarly there, similarly there. So what you're doing is you're confusing the IGBT driver. So the IGBT driver will try and switch and then immediately try and switch again. It's already trying to let through a lot of currents and then it's trying to let through a lot of current. It just can't do it. So it'll just sit there and buzz. Or you hope it sits there and buzz and doesn't just blow up because it's trying to get rid of a load of current. But the misfiring there could cause you huge problems. Also, it's where a lot of production uses the count. It'll wait until 0 point crossing, it'll use that as the counting point. So cross that once, counts once, twice, and that'll be what it uses as a clock. So putting that on a PC is probably going to count that twice. So maybe it's trying to run twice as fast. So what are the solutions? Power factor correction. This can be done traditionally through contactor switching. Usually gives about 2% savings on the kilowatt hour bill. Negates reactive power charges, reduces availability required. BEMA states that you'll get 105 kilos per kVAR saved in carbon emissions. And you really need to maintain any power factor correction you've got on site yearly to make sure that it's still working. Harmonic mitigation uses IGBTs to switch the currents. Basically, it measures the current at each harmonic and then sort of plays it back in antiphase. So it'll inject a current in antiphase to try and cancel it out. This equipment will prolong equipment life expectancy and allow for operation within design parameters, meet grid compliance and reduce losses in cable and transformers. It's quite flexible. You can reprogram it if you have new load to attack different harmonics. So there's a lot more future proofing in that. Power factor can be stored at all voltage levels. Usually seen at LV because it's easy to maintain and install, but we can go on to MV. It's parallel connected, so there's no downtime if we do need to fit it. Harmonic mitigation, again, it's parallel connected, also installed at all voltage levels. Yeah. And then these are the different equipments that we design. So standalone power factor correction, active harmonic filters, and hybrid systems. So that's my talk. If anyone's, are there any questions?
Do you think the national grid is capable of taking the extra load that's required?
Not at the moment. A lot of people are trying to have embedded generation, which just confuses the facts here. It just adds to it. They've got current going towards us. We've got current going towards them. Cables there need to carry both. Yeah.
Imagine when they start them arc furnaces up in Swansea.
Well, yeah, well, this is it.
Lights will go out in Swansea.
Well, they're going to have to switch off Port Talbot. I mean, it's a. Really?
Yeah.
Oh, right.
Metal Racing put a 42 ton in, make shot in Bilston. 25 years ago? I can't remember. It's got to be 25 years ago. And as soon as I turned it on, the lights went out in Bilston.
Yeah, it just took so much.
Arc furnace. As soon as I struck it up,
Everything else went out. Yeah, I mean,
brand new plant as well.
see, 25 years ago.
Cables in.
Yeah. Yeah, but if the, like you say, if the supporting structure isn't there, like if they haven't got it at the MV or HV,
Yeah, I mean, it was early days in them, you know.
Yeah.
I mean, we were using 7 ton, 12 ton arc furnaces.
Well, this is it.
42 ton.
Well, 40 tons arc furnace megawatt is that? I mean, that's huge, isn't it?
It's huge.
But if they didn't do the calcs right, say it was like working at 0.6 power factor, you're almost doubling the kilowatt rate. Sorry.
What worries me is anybody considering?
No.
They're not, are they?
No.
There's nobody.
There's no one in charge. Well, this is what
knowledge to be able to.
this is what I was saying at the start, because they've disconnected the generation and the grid and the network operators from each other. There's no linked up thinking. No one's thinking about it. Just no, that's my little bit.
We used to have dual control, so I could take care of them, put it on together, and that's how we managed it.
Yeah.
But even then, power supply to the family wasn't good enough.
Yeah.
You know, what chance you got if you can't get the power supply?
I think these days, because there's been a reduction in heavy industry, you probably would get the power supply. The problem you have is that there's so many little commercial stuff. Oh yeah, Christ, yeah, don't go down that road. Yeah.
Just a question I wanted to.
Yeah, I'd like to say yes, no, everything's wonderful, but
I'm just putting into it.
yeah.
And you can't melt iron ore in an arc furnace. Make steel. It's not possible. You can only make steel out of
From
iron ore
recycled.
So
Yeah.
it's got to be recycled scrap. And you can imagine what different effects you're getting in the furnace with the.
Yeah, the actual control you need for different sort of stuff. Yeah. Well, I think that's where perhaps these days they've got better control, if you like, but they've lost the expertise. So, yeah, someone who can watch it and go, oh, I need to do this. They lose
They're
that.
going to get electric power for it as well, is it?
So all those electric vehicles are going to plug in to charge the system up. That's what it's going to be. But, any other questions?
Just, and surely it's the power company's interest to go out and tell people about this.
Uh,
Do they?
they don't. All they care about is, kilowatt hours. That's all they want to sell you, just kilowatt hours. We're dealing with someone in South Wales at the moment who've got an issue with harmonics, and we told them to put a K-factor transformer in, which is just a transformer that won't see the losses from harmonics. And the electricity board won't pay the extra for it. So they're telling Welsh Water that they have to pay the extra because they're not prepared to put in a transformer that want to run the load. And that wouldn't have happened 25 years ago. The electricity company would have gone, you want to buy electricity? You need this transformer? There you go. Start showing us the money. They just don't care. They want everyone else to pay for it. And there's just so many people in the line now waiting for money. It's horrible. Projects take 6 years. That should take 6 months. It's frustrating, as you probably tell.
Does harmonics affect your power factor?
Yeah, because each current will have its own power factor, if you like. So you'll have some that add to the power factor and some that will take away from the power factor. So what you have is displacement power factor and true power factor. They're two slightly different measurements. So displacement power factor will be kilowatts over kVA, which is the traditional way. And true power factor is the addition of all the harmonics. Clever thing then is to go, how many harmonics do you want to do the additions to? Do you want to do it to 25, 50, or 100? So this is where instruments are quite canny in that some instruments go, oh yeah, it's true power factor to the 25th harmonic, where some other ones will be up to the 100th, and so it'll be a slightly different value. At the moment, we don't see much difference, but with the greater THDV, you'll get a greater displacement between the two. 25th harmonic is a fundamental is 50 hertz, or 60 hertz in America. So the 25th harmonic will be 50 times 25. So whatever that is in hertz, it's a lot easier for us to just talk about, the 25th harmonic or the 100th harmonic rather than 50k hertz or 150 hertz. So the fifth harmonic is usually quite an important, for inverter drives, that's usually quite a heavy current for us. So we'd say, fifth harmonic is 250 hertz. It's just easier to talk about.
Did you work through the coal miners?
Excuse me?
Were you in business during the coal miners?
Power capacitors work. Yeah, power capacitors work, yeah.
When you got electric furnaces, channel furnaces, all in metal, and the power went up. And you needed to generate electricity by other sources.
Right.
We had a massive diesel engine generator on it.
Yeah.
To try and keep the loop through. And I was just wondering, we were on New Cross electricity supplies.
Yeah.
So it was never turned off, but it did go off.
It dipped. Yeah. Well, I know they were load shedding loads and loads in those days. Yeah, that was a bit before my time, but talking to the guys who, but they were using the power factor correction then to support loads that they didn't use to support. Yeah.
I was just wondering, does the addition of more than one transformer in a circuit have a cumulative effect on the impact of the harmonic?
Not really, because what you're doing there is the transformers are basically a source of current for your system. So because they're joined for voltage, the voltage will stay the same across those two transformers. And really that's why the network operators are so worried about the harmonics on those, because it's the voltage that changes. So the voltage then will go onto their grid through both of those transformers. So it doesn't, it's a really good question, because most of the time with components, you go, all right, I'll split the current or I'll split the voltage. Whereas in this instance, it doesn't. It basically goes, right, you've got this much harmonic current, this much resistance on your bus bar. This is the voltage that the harmonics are going to generate. So it's the current that induces the voltage. So it depends what resistance basically is between those two transformers. If it was easy as that, everyone would be banging in transformers all over the place. But it doesn't. Yeah, but with the LEDs, they've also got the disadvantage of a leading power factor. They've got the harmonics and the leading power factor. As soon as you get to a certain amount of LEDs, people are finding that there's so much harmonics on there that you can't switch on the next LED. The driver just won't accept that. But a transformer wouldn't help you there. You have to get rid of those harmonics somehow. So that's where the filtering comes in, whether it's passive or active. What I didn't want to do is come and give you a hard sell on the active filters. I just want to give you sort of general idea of what was going on. So. Okay, thank you very much.
I'd like to thank you very much for a great technical session. So